Hi, nice to meet you. My name is Jongmyeong Kim. It is really honored to speak in front of you guys. Thank you for your invitation. Let me start. I will talk about the ABP estimate, Alexandrov Bekelman-Puch estimate on manifold, especially for nonlocal operator on manifold, which is my area. Let's start. So I will briefly talk about the classical maximum principle for elliptic operator. So when the operator is like this, the typical uniformly elliptic operator, then we have a maximum principle, like the maximum happens on the boundary. The proof is really easy. Like you just assume that the maximum point, then you have a the paraboloid happening on second derivative and 0 on the first derivative, and you decide the c, sine of c, and positivity of u, then you have a contradiction with a small technique to deal with the equal part. So, and you also have such a priori bound estimate, which is for a non-homogeneous problem, that a really similar thing with f on the right side. Okay. I will skip the proof part. Now I'll talk about general solution. So there is two ways to understand the elliptic operator. One way is a so-called divergent form. So when deciding the elliptic operator, one have this divergent type. Then by using integration by part, one can define a weak solution concept like this. So like U is defined by the integration by part technique. Then there is also such a priori bound or maximum principle. You can prove. You can find a book in many books, and the reason why we want such a maximum principle is that we can reach such a regularity. Actually, in divergent case, you don't need a maximum principle to reach the whole regularity theory. But anyway, the small goals like PD people regularity people want to have is a regularity. So what is regularity in this case? Like order regularity. So this is. So if U is a weak solution, then the goal is they have a Felder regularity, and the small setback is a Hanach inequality. So Hanach inequality is something that bound supremum U by infimum U. So it means some kind of rigidity that solution should satisfy, that the supremum cannot be big enough if U is solution. So they should be lead closed, and this leads to the Felder regular, the Felder continuous. Okay. So I will talk about classical ABP estimate. So if F is a super solution, so if you are not familiar with the super solution or sub solution, you just think it as a equal F. Okay. So U is just this non-homogeneous equation, solution of this non-homogeneous equation. Then the ABP estimate is saying that supremum of U is bounded above by information of f. The a priori bound you said before, the similar result, but a little bit of more details here, like, okay, what is gamma u, right? This is called envelope. I will introduce later. And since I assume the boundary condition, so actually if you add the boundary here, then it's really similar to the classical a priori bound, right? So it's like continuation of that spirit.
What is minus over there? U minus?
So it's like you cut the u, like a maximum of 0 and minus u. So so actually it's like minimum, infimum of u.
Okay.
So this is just sign changing problem. Like if you choose here, if you choose greater or equal sign, then people call u satisfy a sub solution. Then in that case, this is plus. So like sub solution, maximum principle, super solution. Actually, it's easier to understand as a minimum principle, like minimum happen on the boundary. It's like you draw this picture or you draw this picture. So this is positive case and the maximum happen on the boundary, and this picture is minimum happen on the boundary. But it's just sign changing, right?
Yeah.
So like if you consider minus u, then you sign change this part. It's just sign change. So it's a maximum principle. Some people call it still maximum principle. Some people prefer minimum principle. So u minus is like maximum 0 and minus u. So it's like if you like this, then like this.
Okay.
So it's a technical detail thing. So it's hard to express right now, but you can see in the book or see in the proof, see in the paper, and it's really easy. It's just a little bit of technique thing.
So you should also remind me what is B1?
It's just the ball with radius 1.
Oh, ball with radius.
Yeah, it's ball with radius 1. And so the first question is why do people want this? Oh, of course, it's a maximum principle, so it's a good one. But why do people, especially for Laplacian, like for Laplacian, there's a classical a priori bound we already had before. The reason why is that this technique can be continued to this type of operator, like aijx multiplied to the diju, which is you cannot express this operator as a divergent form. You cannot di and dj inside of, like you cannot put a divergent structure on this one. So still people, the normal people like me think that this and this should be similar somehow, right? Like we think, even though it's not non-differentiable, but if you just Leibniz rule, then there's a top order of aij, and there must be some low order, so they should look similar, right? Even though we don't have a divergent structure. So people still think that even though the U is a solution of this operator, U should behave qualitatively similar to the weak solution case, right? So in this case, the famous Moser technique, doesn't work in general. So that's why people develop this ABP estimate. And from this one, there is a typical routine, and one can reach to the Hölder regularity. Like if U is a solution of this equation, U should be Hölder regular continuous, like Hölder continuous. So that's the spirit of regularity theory. Like the easiest example of regularity theory is a harmonic function, right? Everyone knows that harmonic function should smooth, right? Even though they start with C2, you know it's smooth. That's the spirit of regularity theory. We don't have enough regular, we have information that it satisfies the equation, then so what? You should satisfy some necessary regular. So we will get in this local equation, it is
But just a stupid question. AIJ has better regularity more than everything you will test.
Yeah, AIJ usually it's a continuous.
You can expect the C1, then you can basically rewrite in terms of divergence. Can you write in terms of divergence from some first order term in U?
If AIJ has enough regularity, then both are same. Yeah, then it's like you can speak with this language, you can speak this language, it is okay. But what people will concern is like AIJ is just continuous. You cannot do it. You cannot. Then they two are different. So you cannot speak with those language, those technique model, result model technique. You cannot apply it. Okay.
Thanks.
Okay. And so I will talk about the terminology. So I will call the set X which satisfies this as a contact point. Okay, I will speak more. Okay, I will briefly speak about history. So like 1960s, 1980s, there was those classic ABP estimate and Hanach inequality. And Hanach inequality usually means Hölder regularity. So the Hölder, this gives the Hölder regularity naturally. So this is for local operator on Euclidean space. And I will later say there is also a regularity result for non-local operator like this. And there is also a local operator on Riemmanian manifold case. Like the question is like this: if U is solution on some manifold, like solution of Laplace-Beltrami operator, then does such a regularity result still hold or not? It's a question of these papers. And there is some attempt to define non-local operators, non-local elliptic operators on manifolds like this. Okay. Anyway, so now I'm talking about some terminology like viscosity solution. So there was weak solution for divergent case, right? So U is W12, like U is not C2, but you can still say it is a solution of divergent case. So how do we define a solution for this case, right? Like we don't have a divergent structure, we cannot use integration by part, right? So what is such a weak concept of solution? That is viscosity solution. So we say that you satisfy the viscosity solution when for all phi such that U minus phi has a local minimum and such phi satisfy the equation. Like you are passing the quadratic information of f to the phi, right? So like when U has like this, and when phi touch above and phi is C2, then you can test the phi, right? And if all such phi satisfy the equation, then you are saying U is a viscosity solution, even though U is a C. Like you are starting with this U and you upgrade the regularity. Like you will see that U is C alpha later. So it's a regularity theory like that. Minimum regularity, you upgrade regularity. So I will define the concept of envelope. The gamma you just said before to define a contact set, contact point on contact set. So it's like this, and there is a V in this case, right? V is like the red shape. Then you think about every hyperplane lives below the C, and you move up. Then there is a time you contact the V, right? You move up like this, you move up like this, elevate. Then take every supremum of L, the hyperplane LX, like then you will make some kind of the blue shape, right? Like you think every slope, then you will see this blue one. Okay, so the reason why, the heuristic reason why people consider gamma is convex, and gamma give a maximal slope of this V. It will give a kind of maximal slope information. And one will consider a Pucci operator. So this is, if you're not PDE people, then this is just a class is not familiar. So just uniform ellipticity. So this is like you choose maximum and minimum of such a case. Like the spirit is like, we think that this operator and this operator, just 0.1 difference, right? Like 1.1, 1.2. It should behave really similar, right? Like that's the intuition, right? So try to deal with these two in one sentence. One consider a Pucci operator. Like this is extreme case. Like when you think about saddle point, saddle thing, this is extreme case. Like you have a very bad minus saddle and very bad plus saddle. You are considering those maximal case and consider the class. So if you are not familiar with the language, it's just a Laplacian, okay? Laplacian are inside of this one. So it just want to deal with the variant of Laplacian. One considers Pucci operator and class, okay? If you're not familiar, just think about Laplacian. Okay. So I will briefly talk about the heuristic proof of those ABP estimates. So first, lemma 1 is U is just C2. U is not solution in this case. Then one have this one. So this is why one consider the envelope and the contact point. Okay. And the classical LBP estimate is just if U is solution, then you can change the determinant part of information of S. That's just the ABP estimate. The proof is a little bit hard in detail, but idea is really easy. So you consider the set of all slope, like like this. You consider all the set of slope. And as I said before, the maximum slope you can find on the envelope. And if you restrict the size of domain like here and here, then you consider the triangle. You know the slope, you know the domain, the size of domain, like diameter, then apparently you know the height, right? So that's why we have a information of supremum of U. That's a heuristic idea, really the heuristic idea. The details are in the book, okay? So like this, the supremum of U is the idea of slope, like this, and you change this to the integration, and you use the change of variation formula here, then the determinant appear really naturally. That's the proof of lemma 1. Okay. That's why we consider actually the contact point, because on the contact point you know the slope is du because it's contact, right? Actually
But we always assume U is at least C2 in proof here.
You are correct, because I cheat a little bit. But there is a technique called Jensen approximation. So you first start with C2, you prove everything, and you show that there is a technique called Jensen approximation. Then you somehow show that as epsilon goes to 0, then they converge and all the property converge.
I see.
That's why I abuse
How is
them.
the integral of second order derivative related? Before taking limit, after taking limit, are there any relation for that approximation?
Yeah. There is like a little bit of epsilon. The norm of Hessian is differed by epsilon. It's like that. Yeah. That's right. Or some technique I will later actually show that such a gamma is C11. It's a similar spirit, but they show that this gamma is C11. So, and use the gamma here, they just prove the thing, but they are basically same. Like they look different, but they are same. Like, since you have a Jensen approximation, you know that this gamma will C11. So if you prove that this gamma is C11, then you probably have a Jensen approximation. They have a same information. Okay. So that's the point. Like like people say first a priori estimate, like U is C2. They assume U is C2, but they prove in a sense that Jensen approximation will work. And after they prove Jensen approximation, and they remove the priori estimate. That's the most of the time routine. Okay. And to prove the classical ABP estimate, there is two different methods. So easiest one is, you know that this is true. Then somehow you will know that Diju has some kind of upper bound, right? Then determinant of Diju should have some kind of upper bound. And that's the first proof, which is the classical one, easiest one. But this method is saying that I will use a Jensen approximation. But for another method is I said before that showing the gamma is C11 is like this. So actually, one wants to control the Hessian of U, right? That means gamma, which is almost similar to U. The Hessian of gamma or Hessian of U should be like this, the second term, the second order term and their coefficients, right? So if one show this kind of quadratic control, then one have a determinant bound like this. Then you plug into the here, and you will have a ABP. Okay, there's a 2-bit method, and okay. Anyway. So I will skip this proof. It's since this is a proof when one doesn't want to use the Jensen approximation, so one rely on the definition of viscosity solution heavily, and it's a really technical, so it's not not good, I think, for general people. Okay, now one reach so-called L1 density theorem, that with such an ABP estimate, one can achieve such like this, like U is solution of Laplace equation with non-homogeneous term F, then, and if U satisfies some kind of condition, then their distribution has a bound. That's the so-called distribution theorem. And you iterate those distribution theorems a little bit, then you have such a L epsilon estimate. So, like this, a little bit of distribution, but you know the relation of the value like this. And what I want to say in general is that this proof rely on the Calderon-Zygmunt decomposition of Rn, like the dyadic decomposition. And and with this L epsilon estimate, it is quite common that one will have a Hanag inequality, and from this Hanag inequality, one will have a Holder regularity, like iteration lemma. It's like not on Evans, a little bit of elliptic elliptic PDE book. You will see this routine. It's really the routine from L epsilon estimate to reach the Holder estimate. Okay, that's just technical and PD technical thing. Okay, now I will talk about non-local elliptic operator. So as before, one wants to consider class S. So what was class S? It's like you want to deal with 1.1 problem and 1.2 problem, right? Like it should be qualitatively similar. So if you are not familiar with that, ignore everything. It will be the fractional Laplacian. So like you remove the lambda here like this, and you plug K with this one, then this LU, typo, the LU, this L is called the fractional Laplacian. So the local case was Laplacian, right? That was for Laplacian, and this case I will call fractional Laplacian, and I will justify terminology later. Then why one call this as a non-local operator? It's quite intuitive, right? Because when you want to compute the Laplacian, you just want a second derivative information on one point, right? Partial xu plus partial yu. Like you just want a partial xu and partial yu. But when you want to when you want to deal with this operator, you need to integrate every value of u on the domain. So that's why some people call this as a non-local elliptic operator. And these two are same because ux plus y, ux minus y. Like you have this one, and you have this one, and u minus 2, and you have a ux plus y plus ux minus y minus 2ux using symmetry. Okay, so these two operators are same.
Does this reduce to Laplacian in some special case, for some special case?
Yes, if s goes to 1.
S goes to 1.
Yeah, this s goes to 1, then it converges to the Laplace. That's what I showed you before. Like, so why people call this as a fractional Laplacian? So this is just a integral definition form we just saw before, and one also can define by Fourier transform. So you know that the Fourier sine of Laplace, remove s, and it should be 2, right? The sine is 2. And the singular definition we just had before, if you Fourier transform that one, then you calculate Fourier transform like this, and you plug out some kind of a conceit. Then you compute those values. Then you set some constant, multiply the sine of 2s. So it is true. That means now it's more clear for some of you guys, right? Because it literally fraction the sine of Fourier, right? Like s. One also can see a definition by this calculation that we know this we know this equality, and by using spectral theory, the fractional Laplacian seems like it satisfies this one with et Laplace is a heat corner, the heat semigroup. Then you do a Fubini theorem, and you multiply dt first with heat corner here, heat corner. Then you compute this one, just compute. Then you end up with a absolute value z n plus 2s, which is corner of this one. Okay, so there is a paper that these three definitions are equal on some function space, and actually there is more definitions. There is a 10 equivalent definitions. Okay, and also there is a probabilistic interpretation for this one, like because Laplacian heat equation, right? And heat equation is connected to Brownian motion, right? And Brownian motion, it is infinitesimal of a neighborhood jump in the Zn, right? Just a neighborhood jump. Then you might consider a probabilistic jump that do not just move by just one edge. If you consider a jump like 2 edge, 3 edge with some probability, and you make infinitesimal model, then it will converge it to alpha stable Levy process, and it is connected to this fractional Laplacian. There is also a probabilistic approach, and there is some probability guy who work on the regularity or the heat corner or this Levy process things. Okay, I will also consider such a Pucci extreme operator, but it's just technical. Okay, fractional Laplacian. Okay. So and on our end, we use same envelope like that one. You consider every slope and you elevate and you gather the stream of that value and you have an envelope in this case. Okay, but there is a little bit of problem on non-local case, on non-local non-divergent case, that until now there is. So this is the proof, right? You see before. So one bound supreme U by this regime, but at the classical case and local case, you just change this part by the direct information on the points, right? Like direct information on the point, like this or this. X close to x0, so this means the local information, and this is also local information. But on non-local case, it is up to date. No one can do the local information on the contact point. One only can get the information on near the contact point. That's the thing one should overcome right now. That's the open problem. So, but still, we have a inequality still. So we can still write down the ABP estimate in this version, and people find out that from such an ABP, a little bit of weak ABP estimate, but one still get the Felder regularity. So this is not a perfect version, but it's still okay to get a regularity result, so people use this. Okay, so this is a part of the technical lemma for this, and you see that here already that the theorem should be, ABP theorem is written under the near contact point, because this RK is a ring like this, like BRK minus BR plus K, and RK is a converging sequence to 0. So this is a small ring, and you have a measure data of quadratic controllability only on the ring. That's the latest attempt. And why it is enough? Because one can use this half-ring lemma. Is even though you have a quadratic controllability on this ring, but since the gamma has a convex, since gamma is convex, you think about this middle point. Then you can change those measure information inside of this ring with convexity. Okay, like if it's not, so the idea is like this. If it's not true on this, if it's true on this one, if it's true on this one, then from convexity, you say that it's true on this line actually, right? And you can fit in this every line. It's like actually the proof is a little bit of contradiction argument. But the basic idea is like this: you use a convexity, and since you want a quadratic controllability of this one, and this inequality is preserved by convex, like gamma 1 and gamma 2, and this is true for gamma 1 plus gamma 2 over 2. So if one is true on this one is true on this one, then you say that you are true on this smaller ring. That's the half-ring lemma. Like you transform the quadratic controllability on the ring, measure data on the ring, by the perfect data on inside of smaller ring. So this is this is true in whole ball, not a measure theoretic. Okay. So, but I want to point out that since you talk about measure data, so measure means volume, right? Measure means volume, and this picture is heavily depend on the uniformity of volume on Euclidean space. I mean you have a double length, like one length, two lengths. You know that size is 4, right? Like this, the volume of these objects are uniform. Like you scale twice the picture, but the relative ratio of these objects are same, right? That's what happened on the Euclidean space, right? They don't have a distortion. Anyway, from those two lemma, we get the quadratic control of U by F, and there is a Calderon-Zygmunt theorem. This is Calderon-Zygmunt decomposition, and you use Calderon-Zygmunt decomposition, then you reach the ABP estimate. So supremum of U bounded above by information of F, but it was integral, right? It was integral, ln norm of F. But since this one use Calderon-Zygmunt decomposition, that means you replace the integral, because information was on the near contact point. You want to fetching those near contact points. You cannot do integral in this case. You add on every such a small piece. So this is why it's a weaker version of ABP in nonlocal case. Integral is a summation, right? You cannot reach the integral in this case. You only can reach the summation. Okay.
And can you keep on decomposing the same cube to make the estimate, right? It's not finite.
Yeah, that's and the Calderon-Zygmunt decomposition is that it stops, right? It has such a stop, like you keep digging, then it has some stop point that satisfy the property. That's Calderon-Zygmunt decomposition, right? I understand why. Theoretically, if one can keep doing, then you think you can do integral, right?
Right.
Yeah, but that's I know the reason, but I forget. That's I'm sorry, I knew why it's not possible, but I forget the reason. I mean, the big, like computationally hard paper. I missed that one. Sorry. If I remember, I will talk to you back later. Okay. Anyway, it's still possible that from this ABP estimate, this version of ABP estimate, one can still get a Holder regularity. So one can say that non-homogeneous, like Poisson equation for fractional Laplacian, one have the solution should be Hölder continuous. That's the conclusion of this project. So from now on, I will talk about my result. The question is simple. What happens if you consider such problem on manifold? Right? It is a little bit different than local case because such a local operator, since that is local and manifold is locally Euclidean, so it's really easy to conject that most of qualitative things comes to same, right? Like you consider the harmonic function on manifold, you still think that is smooth, right? The difficult part is the coefficient dependency kind of thing, right? The Hölder continuity is qualitative thing, so it should be similar on Euclidean space and manifold or local operator, right? But in this case, it's a little bit different, right? Because the operator needs a whole integral. So even for the qualitative question, it's hard to answer, right? One cannot sure about further continuous of the solution on non-local operator or manifold, right? So that's a little bit of different point than the local case. So I cannot talk all the details, but I will talk the difficult part when I convert problem to the manifold. Okay. So the first question is what is non-local elliptic operator on manifold, right? How do we define? And second one is about the envelope. I will discuss later a little bit. And third question is, do we still have a Calderon-Zygmunt decomposition on random Riemmanian manifold, right? And the fourth question is about the calculation we did before, like quadratic control on the near the contact point. Is it still possible, and how the value change, like boundness, like dependency on the coefficient, how it will change, right? Okay. And I will say about the case that the manifold is complete with sectional curvature bounded below by 0 with such an additional assumption. And I want to say that this is always true for manifolds. But what I want to say is that to track down the dependency, okay, like it's you can find A1 depend on injectivity radius of n, but then if you write down everything on the injectivity radius, then it's a little bit dirty. So I just want to track down more clear on the coefficient. I introduced this condition, and this is a little bit, it's more stronger than it's a more important assumption. Like you can compare volume of ball with a uniform coefficient, okay? But still, these two are not that strong conditions, okay? I think everyone knows injectivity radius here, right? It's just you consider the Gaussian exponential map and the maximal radius that such a projection is injected, right? The example is sphere, right? The sphere, the tangent space on the sphere is infinite, but you project, and a small amount of area is just injectively projected, right? The other part winding twice, and that overlapping area is one to ignore, right? And the radius, that radius is injective radius. That's like the other, like you ignore all the overlapping part, but the maximum radius is injective radius. And also I consider the class L as before, but as before, like class L gives a notion of fractional Laplacian, right? So in here, it was absolute value x minus y n plus 2s, right? Distance n plus 2s was it on Euclidean case. Now I use a volume of ball multiply distance 2s. So it has the same order. Distance n plus 2s, distance n is almost volume, so volume multiply distance 2s. I use this as a corner, okay? And I won't say this is a fractional Laplacian. This is a non-local elliptic operator. I don't know what it is, but this is not fractional Laplacian, like, because if you consider random Riemmanian manifold, you have a Fourier transform. Like, as far as I know, there is like two kind of attempt to define Fourier transform, and those things are always defined in a very abstract language. You cannot compute. As far as I know, it's impossible to compute, I think, right now. So so people try to use this one, like probability case, like Chen, Kubagai, Wang. They use this one, and Gregorian also use this one as a just non-local elliptic operator. So I also use this one as a non-local operator.
Maybe a simple question: how would you define the operator t sub x z? What is exponential z minus exponential?
It's a u x minus y, like x plus y and x minus y. I want to go back by this one.
But exponential map is the one in exponential x z is a point on the Riemmanian manifold. So how can we do a subtraction? Since this is on the inside of injective series, it's just I just we prove that everything.
yeah. I just identify everything. This is basically the Euclidean case. I mean, the purpose is really obvious when I select the injective, the sectional curvature bounded below by 0, right? Like it's in a volume, in a point of a volume, it's dominated by Euclidean space. So every pictures are Euclidean, so it's possible. Like just notation is like those two identifications. If I write down everything, is so much, so much hard. So it's like just you push back, right? And so this is the answer for the first question. So I will not say this is a fractional Laplacian. It is some non-local operator, which I feel like it should be similar to fractional Laplacian, but there is not conclusive. That's not conclusive. But still, non-local operator I will deal with. And the second question was about envelope, right? Because when Euclidean case, we think of a plane going up, right? Every plane going up, hyperplane going up. And actually, inside of calculation, what people want to use is a parallel transform. Like the concept when PD guys think of an envelope is that they have a single definition of such a vector on the manifold. Like they want to use that feature, like single vector in every place. That means absolute parallelism, right? Like and in manifold it's not possible, as you all know, right? Like you don't have a single concept of such a direction. Like if it is, then you can split the space by a smaller space multiply r. Right? And if you do everything, that means it's just isomorphic to Rn. So one cannot consider slope, the concept of hyperplane and upping up and the stream U. I mean, you can think of that, but in PD calculation wise, it's unusable, right? So instead of plane, one considers such a distance square like this, and you do the same thing. You do same thing, and and where the information of slope goes, it's like if you contact here. Imagine you contact here, then you consider a map from this point to the vertex. Then actually that gives information of slope. Okay, so this object is doesn't affected by such a parallelism, and also give a slope, information of slope. So it's proper to use on the manifold. So with this distance square, one considered a little bit different envelope. You know this picture, right? You cannot go winding parallel transform on the manifold. So there is no absolute parallelism. The concept of slope that PD people use cannot be true on the manifold, right? So instead of plane, one has to consider distance square. And the normal map is a concept of slope. So finding so going from contact point to vertex point, and that information give a slope as before. And one also have a such gamma that you made from distance square. That isn't convex, not anymore, but you have a smaller error, like R2 error, then it is convex. Right? You imagine that it's not convex because it's not made by a plane, but it's made from distance square, so it's a little bit upper, right? It might go a little bit upper, but still have some kind of regularity. That's we called R2 convexity, minus R2 convexity, or R2 convexity we call. So this convex, when we use half-ring lemma as before, so we can replace that. And there is a Calderon geometry decomposition still on manifold. And actually in this paper there is a number 6 which say that the inside of cell and the outer area of cells are volume comparison, because they want to do the things on volume doubling space. But in this case we don't need to use that. We just have this 5-1. I mean, original paper of Christ 19, they assume the volume doubling space, and they achieve a more on the theorem, but we check that what we need doesn't need a volume doubling condition, so we remove the volume doubling condition and we write down just a 5 consequence, which is a typical Calderon geometry we want to use. Okay? So there is a Calderon geometry composition here. Okay. Now I will talk about the well-definedness of the nonlocal operator, and I will talk about some heuristics when we deal with this operator. Okay. So one can compute that either R2, R square, or dx to z square of operator jump corner j or k is bounded above by r to the 2 minus 2s. So this is by direct computation. But in here, idea is really simple. As you remember, here was ux plus ux plus y plus ux minus y minus 2ux, which if you divide by distance square, then it's this part is d square u. Like infinitesimally, this is Hessian. So what we want is control this d square with corner j, the fraction of Laplacian corner, right? And r square is for the outer part, like this. When we compute LU, you see the small ball with delta is like this one, so it's the d square part. And you consider the outer, the complement of ball, this is r square part. Okay? And those two values are controlled by r to the 2 minus 2s. So well defined, and that's the basic spirit of when people deal with nonlocal electric operator. In smaller ball and outside of ball. You split that two and you compute those things. Okay. But on manifold, there's a small problem that I didn't start with this one, right? I start with actually ux minus uz. And while making this one, it was true if it's a symmetric space, like you just adding symmetric like minus version and divide by 2, and they were saying, but on manifold it's like you can think about opposition point, but in there the volume is different, right? The domain is different right now. It's like because it's not symmetric space. So while defining that, well-defined is might have a problem, right? Because of this part. Like you just consider the symmetric volume as a measure-wise, then that things are same on the Euclidean space, and this is a same on the Euclidean space. But this anti-symmetric part actually, because we define the sectional curvature bound, that it should be living in somehow between this one, right? It's a volume density, like volume density of Euclidean space r to the n minus 1, and sphere is r to the n minus sine r to the n minus 1, right? So in here, so heuristic is like this. When one wants to control this one needs a d square, and with computation of this one, it's a r to the 2 minus 2s. But in here, we only get one distance, right? This only give a distance 1, not distance square. But in here, since it's antisymmetric part, it gives a slope, one more d distance. So this is still well defined by same value, like r to the 2 minus square. So that's a small part. Okay, and from these observations, and if you replace those things from the Euclidean case, then everything is just computation. You just calculate everything, then you reach the ABP space. And it was actually supremum u bounded by some value on S, right? It was a summation for non-local, so it's summation still, but it's a different, like a little bit different, because it's a manifold. You have to get a little bit weaker version of that. But the supremum u, information of supremum u is here. Okay, we just give it to the condition, and you get another inequality. But it's a weaker version of ABP estimate. and apply the Calderon-Zygmunt decomposition, and you will get a Hanach and Holder estimate. Okay, still C alpha, and spring of U is bound above by spring of U, Hanach inequality. You still can get this. Okay. Oh. Okay. So this is a simplified version of what I did. So this was classical case, right? You use just area formula. You get a determinant d squared u. Local case, you just change this one by f. Non-local Euclidean case, I don't know the reason for now, but you only can get the near contact, so you add up by a Calderon-Zygmunt. That was non-local Euclidean case, but on local manifold, how one can reach this one is you change this BR by a contact set of normal map, and use a area formula here, because you use area formula, right, at the red part, from this one to this one. Yeah, this one. It's area formula. So you still use the area formula, then you reach, because it was a distance square. The convex envelope was distance square, made by distance square. You reach the Jacobi field, and if you have a curvature estimate, if you have a curvature bound, there is a Jacobi field boundness. Okay. So in here you use that one, and non-local manifolds, you mixing these two problems together. You cannot get a contact set on. You get the information on your contact set, and you apply Jacobi field estimate on these near contact set, and you still can get the result. Okay. Jacobi field is coming from second variation of geodesic energy. So one can define by this one, or one can define by variation of geodesic energy. Right? Do I have to explain, or I think in geometry class you learned this one, right?
Or you can
right.
You can talk about your main theory.
Yeah, okay. And also there is a Raj comparison principle. This is a Jacobi field estimate, and also from from Riemann curvature you have a volume comparison theorem. So from this one you can get a ring lemma as before, and half ring also same. Because of R2 convexity, you can also get. And since there was no symmetry, I use a orthogonal comparison principle to deal with those inside of injective values, but you still have to control some symmetric points. Because you don't have a symmetry, you have to consider. I use orthogonal comparison principle to deal with that. Okay. So you get the Hanach inequality and Felder. Okay. So that was for sectional curvature bounded below by 0. So my next question is, then what about negatively curved space? Right? That was I thought it's a natural, and I will also talk about difficulties. That what is non-local operator or fractional Laplacian, And envelope, I use same one, so we don't care about this one. Cardinal decomposition, as I said before, it doesn't depend on the volume doubling condition, so it's also true. So I can use this one, same. And the gradient control point is still I have to calculate hard, and those well-defined is it still well-defined? It's also a question, right? So now it's getting dirtier. The jump corner is like is this one. This one, this part. This part is jump corner, right? It was volume multiplied distance to 2x, right? So actually my first attempt was like this. Why not we use same one, like volume multiplied distance 2 square, right? But actually it turned out that you cannot use that. It's not a proper corner for fractional Laplacian, because on hyperbolic space, because of symmetry, you have a fractional Laplacian in this case. Okay, so in this case, this Ks is a proper jump corner for fractional Laplacian in hyperbolic space, and in here K is a modified Bessel function, and this operator means you derivative first and divide later. Okay, and so if n is 3, it's quite not long, but if n is 5 or 7, then you have a long computation by a recursive relation of modified Bessel function. Okay, so it's difficult, right? It's a dirty, but anyway, the asymptotics are like this. Near 0, it's volume of distance 2s, right? Near 0, it should be similar. Manifold is Euclidean space, even though hyperbolic space, right? So the corner is volume to the distance 2s. But near the infinity, it behaves like this, and it should be somehow true, right? Because hyperbolic space, its volume density is sine hyperbolic n minus 1, and it exponentially grows, right? It grows much faster than polynomial. So this jump corner should behave like this. It's also intuitively right if one considers the volume. And somehow, if you divide by a volume, then this is volume density, right? N minus 1. Sine n minus 1 is sine hyperbolic n minus 1 is volume density, and somehow tangent hyperbolic s come up, because intuitively like this. You integrate the polynomial of r to the n minus 1 is r to the n, right? The polynomial change, like you multiply r1, it's a integration. But for this one, if you integrate this function and compute the asymptotic behavior at the infinity, then there is no polynomial r coming from. Still exponential n minus 1. Okay? So r to the n minus 1 r to the n minus 1 integrate r to the n, but sine hyperbolic n minus 1 integrate. It's really, you cannot, I mean, I think you can, but it's really dirty, but asymptotically. Sine hyperbolic n minus 1, and at the infinity, r doesn't come So it's somehow proper to consider tangent hyperbolic R because it behaves near 0 R, but it goes to constant at the infinity, right? So this also behaves like R at the origin, right? From Husserl class. So origin is R to the n because n minus 1 R to the n, but at the infinity it should be exponential n minus 1. So it's a proper one to consider the constant at the infinity. That's why this part actually somehow behaves like a volume. Then here we suddenly know that distance 2s is a little bit wrong, the conjecture that we had on the sectional curvature 0 case. Okay, it somehow it's a little bit difficult. Okay. Now I just use this s as a t over sine hyperbolic t, and this h as a t cotangent hyperbolic t, and this h appears on the Hessian comparison of distance function. This h is that function, and t is like this one. And here I define the I0 and I infinity. It's like, as you said before, distance square, jump corner, integration inside of ball. R square, jump corner, integration outside of ball, right? They both were bounded above by R to the 2 minus 2s, the well-defined case, right? But in this case, this value is not represented by elementary function, not anymore. So I just use this value, but it's bounded. I showed in the paper, but this is bounded, but it's not anymore. But it's if you are familiar with Euclidean case, it's R to the 2s. It's a brother of R to the 2s. Okay. Okay. Then there is a comparison of Hessian comparison principle, Hessian comparison theorem with h of this function, right? And then I can get such an information that such an I0, I don't know, it's not elementary function, but still this value is decreasing. So it was R to the 2s, R to the 2 minus 2s, so it is in the past case R to the minus s, so it's decreasing, right? I just extract the decreasing property. I don't know how I don't know how to write down it. It's so complicated. Okay? And I know how to compare those I infinity outside of value and inside of value by this h function. Okay, I get this lemma, and I get the limit behavior of s because it is important, because I will explain later again that this regular nonlocal elliptic theory, people has one more question about this theorem. Like, what happens if you push s to the 1? S was the fractional coefficient, right? If we are saying about fractional s, and s to the 1, you think like it goes to Laplace, right? So the question is like this. So people call this as a robustness principle. That so okay, you get a non-local properties like inequality, Hanna inequality, Helder estimate. Is it still preserved? Those inequality doesn't blow up as s to the 1? It's also a question. So like so then people say that this fractional calculation somehow happen on the local case, right? Non-local to local. That's the robustness. That's people call robustness, and this is for the robustness computation. And I will say that these results are robust. So this explains the Laplacian on hyperbolic space. Okay, Laplace-Beltrami operator on hyperbolic space. Okay. I will remark about the local case by Wang and Zhang. They did this ABP estimate on rich curvature bound on local operator. Okay. But for me, I cannot do for rich curvature bound. I only deal with the hyperbolic space, and if you remember that the size of ball bounded by information of f is inside of here, and the summation, this is this size of ball bounded above by information of f as a summation. Is this size of ball bounded by information of f as a summation. This is ABP estimate. And one also need to do half-ring lemma, as I said before, but the technical problem is that, as I said before, if you scale this picture twice, lengthwise, twice in the hyperbolic space, then the volume behaves different, right? Volume doesn't, like, size of ball of radius 2 in hyperbolic space and size of 4, then you can, because it's polynomial, like it's a r to the square, then it's a 2r to the square is 4r squared, so you can cancel the r, right? But hyperbolic space, because it's a sine hyperbolic, you cannot have this one, right? You have to live with those r, but somehow PD people want to kill that one, because if you write down everything depends on r, that doesn't mean anything, like it doesn't give you any information. So that's why one consider a little bit smaller radius by this one. Like you consider a smaller radius and doing this comparison of this size of this one and this small ball like this. But luckily, with this green radius, I can still get the Hana inequality. Yeah, I can still get Hana inequality. Okay. This is a definition of hyperbolic space. There is a famous 2 model on the paraboloid model, and give a metric on the ball. Okay. Anyway, I can compute those things, hard computation, but I still can get the Hana inequality and Felder estimate. And one thing more notice that it is not only robust, like if I push s to the 1, this constant doesn't blow up, and also that if I push kappa to the 0, the kappa was curvature of hyperbolic space, minus kappa. So kappa to the 0 means it's flattening and flattening, right? And this value converges to the r to the 2 minus 2s, which was true on Euclidean space. So this also explains, in a sense, that kappa converges to the Euclidean space. This result also converges to the Euclidean case. So this was somewhat primitive, right? I used just a curvature and comparison theorem you can learn the textbook. Yes, that's what I did. Like, I just want to solve the problem. Okay. Like, I just switch things by things. It's long, but theoretically it's all I said is inside of of the paper. Everything else is just computation. But it was non-local operator, non-divergence form. What I do is technique for non-divergence. And I said before at the very first, like, divergent case, right? Generalized solution, weak solution, divergent, and integration by part. Then what about divergence technique on non-local operator, right? And you can search by Gregorian, Alexander Gregorian, or Chen Kumagai Wang. Those two people are great guys dealing with this area. So I will introduce this case. So consider the locally complex approximatic space with a Dirichlet form epsilon like this. Okay, with jump type J. And the idea of this one is this. When you start to learn Laplacian, you remember this one, right? So-called energy. You consider the minimization of this one, then that solves the this one, right? From energy minimization, you reach the solution of elliptic operator. That's actually what happened on this one. This is energy, in a sense like that, Dirichlet form. Then there is a corresponding operator L, and that is a fractional Laplacian. Okay? Because divergence form, integration by part, you can define the energy. So in this case, like divergence approach, they have a better one, energy. Okay. Now I'm defining a condition volume that volume of ball is r to the alpha, and I will define the condition J is that the shape of jump corner is like distance alpha to the 2s. So distance n to the 2s, right? It was volume to the 2s, n to the n plus 2s, so alpha to the 2s.
Sorry, I need to remind you it's getting late, so would you just summarize your talk quickly?
Okay, sorry. Okay. And there is a condition heat corner estimate. Like, you have energy, you have a corresponding operator L, and you think about the heat semi group, and there is a heat corner, right? And one can define such a jump type heat corner. Then important observation by Gregorian is that if you assume volume, then if you have a J and with additional assumption, then you reach that you have a both side of heat corner estimate. So jump corner and volume is informationally somehow similar to the heat corner, and while they achieving this one, they have to achieve a Feather regularity for near lower estimate. Okay, and while doing that, is one has to get a Fabre-Cron inequality like this, and this is a somehow geometric version of Poincaré's overlap inequality, and they eventually get the Feather inequality. Oscillation means a Feather continuous. Okay, and what I'm now doing is, because in this case this means space is volume doubling. Volume is polynomial growth. You have a, if you double the volume, R alpha cancel, right? So, but hyperbolic space, it does not true. Hyperbolic space, exponential growth of volume. So in this case, I assume the fk tilde like this, and the volume measure looks like this, with sine hyperbolic and tangent hyperbolic, and I achieved the oscillation also with fk assumed. The problem is, originally fk was achieved naturally by volume and jump corner condition, but hyperbolic space I'm trying to do, but it seems a little bit hard because of lack of polynomial polynomial structure. So this is an in progress I'm working on, and in the picture of this one, it may be really important to ask, from hyperbolic type volume and hyperbolic type jump corner, does one can get a hyperbolic jump heat corner, like the original question do? But in hyperbolic space, or many other people only care about volume doubling. Like many papers, if you read the first step, then they assume the volume doubling, and there is not much thing. So I'm working on this area. Like, what about without symmetry? Because the GK condition is connected to the symmetry. So I want to drop the GK condition, or I want to find a proper GK condition, and it's about symmetry and heat corner. And what about other symmetric space except hyperbolic space? If I add the symmetry, then there is many symmetric space with heat corner are known. So that's what I'm doing, like in this area. I mean, I still get a Helder regularity in divergent type operator. Thank you. Sorry for the long time, over time. Sorry.
Question?
So maybe one simple question. In your first result, where do we need the sectional curvature not negative, but instead of sectional curvature bound from below, where do you use that?
Basically, okay. One point is here. I use the volume density, right? Mm-hmm. And volume density you cannot get from ridge curvature. You only have to use sectional curvature. So here one time, and I used a volume, like, because well, I want to find this value, right? And I want to control the volume, right? And here I use the visual normal comparison, but yes, it's a ridge curvature only, right? I mean, but
you use the Jacobi field comparison somewhere.
Yeah, that's also true. I also use Jacobi field, and it's also true if you have a ridge curvature bound. But yeah, route comparison principle, you can do it by ridge curvature. But since I use this strong one, I just assume the sectional one. So like.
But if you assume say the sectional curvature lower bound is minus capital, if you assume the square root of capital times R is always bounded about by constant, so can your estimate still true depending on that constant?
You mean the negatively curved space, right?
The negatively curved space, but the lower bound times the capital R, this is your scale. The square root of your negative lower bound times the scale is always bounded about. Can you can you also?
Sorry, one more time.
The kappa times square root of kappa times r. That one is bounded from far. If you assume that, so if you not allow the capital R to be very big in your estimate, it is still true.
You mean the
If you only consider
kappa r square?
Yeah, that one is not very big.
Kappa is the
lower bound of the sectional curvature.
with a positive value or negative value?
Negative, minus kappa.
Oh, okay. That's actually I yeah, it's like that's actually what I was thinking too. Like if I bound sectional curvature by -1, for example.
Yeah, take your capital R to be 1, say, can you have something uniform? Not equal. Then you don't need the hyperbolic.
No. Hyperbolic space is the space with sectional curvature -1.
But you need the equality.
Yeah. Because that's the point of everything actually. Like in here, regime is polynomial. Like you see the sphere, but you say the volume is smaller than r to the n. So if you double the radius, the volume still doesn't grow faster than Euclidean space. So it's a volume doubling space.
Right.
But hyperbolic space, the volume, if you double the volume, if you double the radius, the volume grows exponentially. It's getting bigger.
Right, but if it doesn't allow the size of the ball to be very big, then the doubling process still holds.
Yeah. That's then many things should in this kind of coefficient. It depends on radius, right? Then yeah, one might. I didn't try because I have to check. Unlike local case, I need to check the outside of the radius because operator itself needs to control inside of ball and outside of ball. Like you want to deal with this area, but the operator itself wants information of outside, right? That's a little bit of different than local case than non-local case. That's why, I think one can write down the qualitative answer, and actually it's like this. I didn't. You have a sharp eye. So here, actually it depends on somehow radius, my version. Because fk tilde is a bottom spectrum, seems somehow this choice of sigma is a sigma r bar, but it was fk, it was sigma is uniform. Like volume doubling space, you can make many things uniform, but not volume doubling space, like volume exponential space, it has such a problem, so I put it in here, so I achieve a qualitative lemma, like Holder continuous. Yes, it is Holder continuous, but coefficients are dirtier. Yeah, that's true. But and actually they behave really different, like because the corner shape is different. It's these kind of things actually say that such a heat corner or Laplace operator give information of geometry. Like analytically, you can read the volume by seeing the heat corner, right? This is I think this is more of your taste than the first version, right? Because energy is really fancy tool. the primitive tool I used before is like really primitive, like sectional college comparison. But in here, we have energy, we have such a more beautiful result. And that's my question, like, what if I see the jump type heat corner on some space with exponential volume growth? Then can I say, okay, this volume is exponentially grow? Can I say that or not? It's like, and this is part of that journey, I would say. Like, if I get a near lower diagonal heat corner estimate from this one, and maybe like there is a surviving condition, and that means after I check that things, I can get back from the volume. That like if I see the jump corner jump type heat corner, then okay, this is the volume is really looks similar to the hyperbolic space. And what about a function that I don't know? That's my problem. I started with PDE. I don't know many examples like which volume grow really faster than exponential. I don't know such a concrete example. That's actually my question. Like if I can see that symmetric kind of space, then maybe I try to get a heat corner there. Then I get I can compute in that case by Fourier transform. I can get a jump corner, and I can maybe try these routines, and so my answer is like this. Even though you choose a small area, you want a small area result, the nature of operator, you need to compute the outside of whole the domain. So somehow it's more somehow more difficult, and after, like, it might be highly likely that the result itself somehow have a dependence on the diameter, maybe. Yeah. So it's
Thank you so much.
yeah. I mean, maybe I can drop this R bar on if I put hyperbolic space here, like assume hyperbolic space, then I might cancel this R bar. But with generality, the current technique, I only get the R bar right now. I mean, it's really bad. If you see this, it's really bad. You have to restrict the area by R bar. Means like if it's 5, it's half. If it's 10, it might be 1/4. Then R is still same. Like it's but the volume doubling space is much more easier because those sigma is uniform. Like you always have a choose half. But I don't know. It seems like it's a limitation of technique, maybe, but somehow it's nature of the space. Like volume doubling space and volume non-volume doubling space has a really critical difference. They behave really critically different. That's what I can say to you, because as a chapter 4, I only do on the hyperbolic space. The reason why I cannot do for like sectional curvature bounded below by -2 and over by -1. Like imagine such a space. But the primitive comparison tools give that volumes are exponential -2r to exponential -r. And those two are really different at the end of manifold. So, and I have to always consider that to well-define the operator. Like if I just put that primitive one to the operator, then that operator gives infinity. Like, oh, you cannot compute this one. Like that means that's why I consider actually this volume and jump corner has a somehow they have to radially, they have to harmonic, they have to cancel, they have to have some kind of cancel relation. I can dominate that by sectional cluster by 0 by Euclidean case, but -1 to -2, I think I need such a like relation between volume and John Connor. Okay, thank you.